We're going to embark on a journey that's both terrifying and beautiful, one that will take us into the heart of the largest planet in our solar system. What would happen if you fell into Jupiter? It's a question that touches something deep within our curiosity, a thought experiment that reveals the awesome power of gravity and the incredible forces that shape our cosmic neighborhood. In this gentle exploration, we'll drift through the layers of Jupiter's atmosphere, discovering what awaits in those swirling clouds of gas and mystery. But before we begin our descent, feel free to comment your time and location below. It's always fascinating to see when and where we're all watching from as we contemplate these cosmic wonders together. Also, the visuals are here for you, but there's absolutely no problem if you doze off midway through the video. Feel free to close your eyes, breathe deep, and let your imagination float through the vast expanse of space. I would love and encourage you to watch the video till the end to discover the incredible physics at play. But there is absolutely no problem if you find yourself drifting off as we explore Jupiter's mysteries. Let your thoughts journey alongside us through the solar system's most magnificent giant. A gentle request that if you find comfort in these peaceful explorations of science, I'd be grateful if you'd consider subscribing and liking this video. It helps the algorithm find more curious minds like us, who have an amazing passion for understanding our universe. Let's begin. Welcome to a journey that will take us 484 million miles from Earth, to a world so massive that it could contain all the other planets in our solar system combined. Tonight, we're exploring what would happen if you found yourself falling toward Jupiter, the king of planets, a gas giant whose very existence has shaped the evolution of our entire solar system. As you settle into this moment of quiet contemplation, perhaps with the gentle weight of evening settling around you, imagine yourself drifting through the emptiness of space, approaching this colossal world. Jupiter looms before you like an ancient god, its great red spot glaring like a cosmic eye that has been watching the solar system for centuries. The planet's bands of swirling clouds stretch across its surface in mesmerizing patterns, a testament to the incredible atmospheric dynamics that rage within. This is the story of what would happen to a human body, to consciousness itself, as it encounters forces beyond anything we experience here on Earth. It's a tale that begins in the cold vacuum of space and ends in conditions so extreme they challenge our understanding of matter itself. But it's also a story about the incredible physics that govern our universe, told with the reverence it deserves and the curiosity that drives us to ask impossible questions. Picture yourself floating in the darkness of space, perhaps having somehow escaped from a spacecraft or space station. The solar system stretches out around you in all directions, but your trajectory carries you inexorably toward Jupiter. At first, the planet appears as nothing more than a bright dot in the cosmic darkness. But as days turn to weeks, it begins to grow larger and larger in your field of vision. From a distance, Jupiter is breathtakingly beautiful. Its atmosphere displays bands of cream, brown, and orange, created by different chemical compounds at various altitudes. Ammonia crystals form white clouds in the upper atmosphere, while deeper layers contain compounds of sulfur and phosphorus that paint the planet in warmer hues. The famous Great Red Spot, a storm larger than Earth itself, rotates slowly in the southern hemisphere, a hurricane that has been raging for at least 400 years. But as you draw closer to this magnificent world, the reality of what awaits begins to reveal itself. Jupiter's gravitational field is immense, nearly 2.5 times stronger than Earth's. This means that as you approach, you're not just falling toward the planet, you're accelerating at an ever-increasing rate. What starts as a gentle drift becomes a headlong plunge into an alien atmosphere. The first thing you would notice as you enter Jupiter's sphere of influence is how different this world is from our own. There's no solid surface to crash into, no ground to break your fall. Jupiter is what astronomers call a gas giant, composed primarily of hydrogen and helium, the same elements that fuel the stars. It's like falling into a sea of gas that extends deeper than the distance from New York to Los Angeles. As you accelerate toward Jupiter, pulled by its tremendous gravity, you would begin to feel the effects of what physicists call tidal forces. These aren't the gentle tides we see on Earth's oceans, but something far more dramatic and terrifying. Jupiter's gravity is so strong that it pulls more forcefully on the parts of your body closest to the planet than on the parts farther away. This differential in gravitational force would begin to stretch your body, pulling your feet toward Jupiter with greater force than your head. At first, this stretching would be barely noticeable, perhaps feeling like a gentle tension in your muscles and joints. But as you fall deeper into Jupiter's gravitational well, the tidal forces would grow stronger and stronger. Your body would begin to elongate, stretched like taffy by the inexorable pull of the planet's gravity. This process, which scientists grimly call spaghettification, would gradually overcome your body's structural integrity. But before the tidal forces could complete their work, you would encounter Jupiter's upper atmosphere. The boundary between space and atmosphere isn't sharp like it is on Earth. Instead, Jupiter's atmosphere gradually thickens as you descend, the gas molecules becoming denser and denser around you. At first, you might not even notice you've entered the atmosphere, but soon the increasing density would begin to affect your motion. As you plunge through the upper reaches of Jupiter's atmosphere, you would encounter temperatures of -230 degrees Fahrenheit. The thin gases around you would be composed mainly of hydrogen and helium, with traces of methane, ammonia, and other compounds. These chemicals create the beautiful colors we see from space, but up close, they would be invisible to your eyes, appearing as nothing more than a gradually thickening haze. The atmospheric pressure at this altitude would still be less than what we experience at sea level on Earth, but it would be increasing rapidly as you fall. With each passing moment, the weight of the atmosphere above you would grow heavier, pressing down with ever greater force. Your body, evolved for the specific conditions of Earth, would begin to struggle with these alien pressures. As you continue your descent, falling at speeds that would make any earthbound skydiver dizzy with terror, the atmosphere around you would begin to change dramatically. The temperature, paradoxically, would start to rise. While the upper atmosphere is bitterly cold, the deeper regions of Jupiter's atmosphere are heated by the planet's internal energy. Jupiter actually radiates more heat into space than it receives from the Sun, a leftover warmth from its formation billions of years ago. The pressure would continue to build around you, and here's where your journey would take a decisive turn toward the impossible. As the atmospheric pressure increases, it would eventually exceed what the human body can withstand. Long before you could reach Jupiter's deeper mysteries, the crushing weight of the atmosphere would compress your body beyond its limits. At pressures just a few times greater than Earth's sea level, human consciousness would fade. the nitrogen in your bloodstream would begin to behave differently, creating effects similar to deep-sea diving nitrogen narcosis. Your thoughts would become clouded, your perception altered, as the very chemistry of consciousness struggled to function under these alien conditions. But let's imagine, for the sake of our cosmic journey, that somehow you could survive these crushing pressures, that some miraculous protection allowed you to continue your fall into Jupiter's depths. What would await you in the deeper layers of this gas giant's atmosphere? As you descend further, the atmosphere would continue to thicken and warm. The pressure would climb to levels found only in the deepest ocean trenches on Earth, then far beyond. The temperature would rise from the bitter cold of space to something approaching the warmth of a summer day, then much hotter still. The gases around you would become so dense they would start to behave more like liquid than gas, a transition that happens gradually in Jupiter's deep atmosphere. The composition of the atmosphere would begin to change as well. While hydrogen and helium dominate throughout most of Jupiter's atmosphere, deeper regions contain increasing amounts of water vapor, ammonia, and hydrogen sulfide. These compounds would create a cocktail of gases that would be toxic to human life, even if the pressure and temperature were somehow manageable. At depths where the pressure reaches dozens of times Earth's atmospheric pressure, you would encounter Jupiter's cloud layers. These aren't the wispy white clouds of Earth's sky, but dense, colorful bands of chemical compounds. Ammonia clouds form in the cooler, upper regions, while deeper layers contain clouds of ammonium hydrosulfide and water ice. Each layer has its own distinct chemistry and appearance, creating the banded structure that makes Jupiter so visually striking from space. The winds at these depths would be unlike anything experienced on Earth. Jupiter's atmosphere is in constant motion, with jet streams racing around the planet at speeds of up to 400 miles per hour. These winds are driven by the planet's rapid rotation. Jupiter spins once every 10 hours, creating powerful Coriolis effects that organize the atmosphere into its characteristic bands and storms. As your hypothetical journey continues deeper into Jupiter's atmosphere, you would eventually reach regions where the pressure becomes so intense that hydrogen itself begins to behave in strange ways. Under normal conditions, hydrogen is a simple gas composed of pairs of hydrogen atoms. But under the extreme pressures found in Jupiter's depths, hydrogen can be compressed into a metallic state, where it conducts electricity like a metal. This metallic hydrogen layer is thought to exist deep within Jupiter, perhaps thousands of miles below the cloud tops we can see from space. It's a state of matter that doesn't exist naturally anywhere on Earth, and scientists can only create tiny amounts of it in laboratory conditions for brief moments. Yet within Jupiter, this exotic form of hydrogen may make up a significant portion of the planet's interior. The transition to metallic hydrogen would mark another impossible barrier for any falling object. The pressures required to create this state of matter are millions of times greater than Earth's atmospheric pressure. No known material could withstand such forces, and the very atoms that make up matter would be compressed into configurations that exist nowhere else in the solar system. But our journey into Jupiter reveals more than just the extreme conditions within a gas giant. It shows us the incredible diversity of worlds that exist in our solar system and the remarkable forces that shape them. Jupiter's immense gravity doesn't just affect objects that fall into its atmosphere, it influences the entire solar system, shepherding asteroids and comets, protecting the inner planets from impacts and helping to maintain the stable orbits that allow life to flourish on Earth. The Great Red Spot, that massive storm we glimpsed from space at the beginning of our journey, is itself a testament to the incredible energy contained within Jupiter's atmosphere. This storm is larger than our entire planet, with winds reaching speeds of 270 miles per hour. It's been raging for centuries, possibly much longer, sustained by the planet's internal heat and the complex dynamics of its thick atmosphere. As we contemplate what it would mean to fall into Jupiter, we're really exploring the boundaries of what's possible in our universe. We're discovering worlds where the familiar rules of Earth-based existence break down, where matter behaves in ways that challenge our understanding, where forces beyond our everyday experience shape reality in profound ways. Tonight, as you prepare for sleep, you can rest knowing that you're safely held by Earth's gentle gravity, breathing air at just the right pressure, warmed by just the right amount of solar energy. But you can also marvel at the incredible diversity of worlds that exist beyond our blue marble. Worlds like Jupiter, where the very nature of matter and energy plays out in ways both beautiful and terrifying. Beautiful and terrifying. The journey deeper into Jupiter's embrace reveals layers of mystery that stretch far beyond what our earthbound experience could ever prepare us for. As we continue our hypothetical descent through this cosmic giant, we encounter realms where the very definitions of solid, liquid, and gas begin to blur into something entirely alien. Imagine falling through pressures so intense that the hydrogen around you begins to glow with its own inner light. At these depths, thousands of miles below Jupiter's visible cloud tops, the temperature climbs to levels that rival the surface of the Sun. The pressure crushes everything with a force millions of times greater than what we feel standing at sea level on Earth. Here, in this alien realm, hydrogen transforms into something that exists nowhere else in our solar system naturally. A metallic state that conducts electricity and behaves like liquid metal. This metallic hydrogen ocean stretches for thousands of miles in every direction. A sea of compressed matter that defies our everyday understanding of how atoms should behave. The electrical currents flowing through this metallic hydrogen layer are what generate Jupiter's powerful magnetic field. A field so strong it extends millions of miles into space and traps radiation in deadly belts around the planet. But our journey doesn't end there. Deep within Jupiter's core, beneath even the metallic hydrogen, lies perhaps the strangest realm of all. Scientists believe that at the very heart of Jupiter, compressed under unimaginable pressure and heated to temperatures exceeding 20,000 degrees Celsius, there may exist a solid core made of rock, metals, and ice. This core, if it exists, would be unlike anything we know on Earth, compressed to densities that make lead seem as light as cork. The core itself might be larger than our entire planet, yet it sits at the bottom of an ocean of gas and liquid thousands of miles deep. It's a world within a world, a solid heart beating at the center of a giant made of gas. The pressures here are so extreme that familiar materials would behave in ways we can barely comprehend. Water ice, if it exists at these depths, would be compressed into exotic forms that remain solid at temperatures hot enough to melt copper. As we contemplate this journey to Jupiter's heart, we begin to understand that we're not just exploring a single planet, but encountering the fundamental forces that shape matter throughout the universe. The same gravitational forces that would crush any earthly visitor are the forces that compress hydrogen in the cores of stars, igniting the nuclear fusion that lights up the cosmos. Jupiter, in many ways, is like a failed star. If it had been just 80 times more massive, the pressures and temperatures in its core would have been sufficient to ignite nuclear fusion, turning our solar system into a binary star system. Instead, Jupiter remains a world caught between planet and star, massive enough to generate its own heat and light from gravitational compression, but not quite massive enough to shine with stellar fire. This near miss with stardom has profound implications for understanding our place in the cosmos. Jupiter's gravity has acted as a cosmic vacuum cleaner for billions of years, sweeping up asteroids and comets that might otherwise have impacted Earth. The scars on Jupiter's moons tell the story of countless impacts that never reach the inner solar system, collisions that were prevented by Jupiter's immense gravitational influence. The Galilean moons that orbit Jupiter, Io, Europa, Ganymede, and Callisto, are worlds shaped by their giant parents' tidal forces. Io, the innermost large moon, is stretched and squeezed by Jupiter's gravity to such an extent that its interior remains molten, driving the most volcanic activity in the solar system. Europa's icy surface hides an ocean kept liquid by the same tidal heating, an ocean that may harbor more water than all of Earth's seas combined. These moons experience tidal forces similar to what would affect a falling human, but spread over geological timescales. The same stretching and compressing that would prove fatal to a human body has, over billions of years, shaped entire worlds, creating some of the most intriguing destinations for the search for life beyond Earth. As we follow our imaginary descent deeper into Jupiter's realm, we encounter not just physical extremes, but temporal ones as well. The deeper layers of Jupiter's atmosphere circulate on timescales that dwarf human experience. While the visible cloud bands we see from space race around the planet in a matter of hours, the deeper atmospheric currents may take decades or centuries to complete their cycles. This vast, slow circulation system carries heat from Jupiter's core to its surface, creating the temperature gradients that drive the planet's spectacular weather patterns. The Great Red Spot itself may be sustained by these deep currents, a surface manifestation of circulation patterns that extend thousands of miles into the planet's interior. The chemistry occurring in Jupiter's deep atmosphere is equally alien to earthly experience. Under the extreme pressures and temperatures, familiar compounds break down and reform in exotic ways. Water, methane, and ammonia undergo chemical reactions impossible under Earth conditions, creating complex organic molecules that rain down through the deeper layers like alien snow. Some scientists speculate that the conditions deep in Jupiter's atmosphere might even be conducive to forming complex organic chemistry, though whether this could lead to anything resembling life remains purely speculative. The constant convection and extreme conditions would make any such chemistry radically different from life as we know it on Earth. As our hypothetical journey nears its end in the crushing depths of Jupiter's core, we're left with a profound appreciation for the incredible diversity of conditions that exist within our own solar system. From the frozen outer moons of the gas giants to the scorching inner layers of rocky planets, our cosmic neighborhood contains environments that span almost the entire range of physical conditions possible in the universe. The journey into Jupiter serves as a humbling reminder of how precisely tuned Earth's conditions are for life as we know it, the gentle pull of gravity that keeps us anchored to our planet's surface, the atmospheric pressure that allows liquid water to exist, the temperature range that permits complex chemistry, all of these factors that seem so natural and inevitable are actually incredibly rare and precious in the cosmic context. Jupiter's extreme environment also gives us insight into the processes that shaped the early solar system. The same gravitational forces and atmospheric dynamics that would prove so hostile to human life are the forces that helped sweep the solar system clean of debris, allowing rocky planets like Earth to form and evolve in relative peace. The magnificent auroras that dance in Jupiter's polar regions, visible in ultraviolet light from space telescopes, are powered by the same magnetic field generated in the planet's metallic hydrogen core. These auroras dwarf anything we see on Earth, with individual auroral displays larger than our entire planet, painting Jupiter's poles with ethereal light generated by charged particles spiraling along magnetic field lines. Tonight, as you drift towards sleep, you can look up at the evening sky and occasionally spot Jupiter as a bright dot among the stars. That peaceful point of light hides one of the most dynamic and extreme environments in our solar system, a world where matter behaves in ways that push the boundaries of physics, where storms rage for centuries, and where the very atoms of hydrogen are crushed into metallic forms that exist nowhere else, naturally. Our imaginary fall into Jupiter reveals not just the fate that would await any earthly visitor to this giant world, but the incredible forces that have shaped our solar system over billions of years. In contemplating the impossible extremes of Jupiter's interior, we gain a deeper appreciation for the delicate balance of forces that makes our own world such a rare and precious oasis in the cosmic ocean. The gas giant stands as a testament to the incredible diversity of worlds that populate our universe, a reminder that beyond our familiar blue marble lie realms where the very nature of matter and energy unfolds in ways both beautiful and terrifying, where the fundamental forces of physics play out their cosmic drama on scales that dwarf human experience and stretch our understanding to its very limits. Its very limits. The deeper we venture into Jupiter's heart, the more we encounter phenomena that exist at the very edge of physical possibility. As our imaginary descent continues through layers of compressed matter, we find ourselves in regions where the familiar laws of chemistry begin to break down entirely. The hydrogen around us, crushed to densities that exceed anything found on Earth, starts to behave in ways that challenge our most basic understanding of how atoms interact with one another. At these crushing depths, perhaps 15,000 miles below the cloud tops we first encountered, the temperature soars to levels that would vaporize any known material from Earth. Yet paradoxically, the immense pressure keeps everything in a state that's neither truly liquid nor gas, but something altogether more exotic. The hydrogen here exists in a plasma state, where electrons have been stripped from their atomic nuclei by the sheer violence of the conditions. This plasma ocean conducts electricity with perfect efficiency, creating vast currents that flow through Jupiter's interior, like rivers of liquid lightning. These electrical currents generate magnetic field lines that twist and spiral through the planet's core, creating a dynamo effect that powers the magnetic field we can detect from millions of miles away. The same magnetic field that creates those spectacular auroras at Jupiter's poles has its origin here, in these impossible depths where matter exists in forms that have no earthly equivalent. As we continue our theoretical journey toward Jupiter's center, we encounter temperatures that climb beyond 20,000 degrees Celsius, hotter than the surface of many stars. At these temperatures, even the most exotic forms of matter begin to break down. The distinction between different elements starts to blur as atomic nuclei are stripped of their electrons entirely, creating a soup of charged particles that behaves more like the interior of a star than the inside of a planet. Yet Jupiter never quite achieved the conditions necessary for stellar ignition. The nuclear fusion that powers our Sun requires not just extreme temperature and pressure, but also sufficient mass to maintain those conditions over cosmic timescales. Jupiter fell short by a factor of about 80, leaving it forever suspended between planet and star, generating heat through gravitational compression rather than nuclear fire. This internal heat source has profound implications for Jupiter's behavior and evolution. Unlike Earth, which receives most of its energy from the Sun, Jupiter generates nearly twice as much heat internally as it receives from solar radiation. This internal furnace has been burning steadily for over 4 billion years, slowly cooling and contracting as it radiates energy into the cold vacuum of space. The heat flowing outward from Jupiter's core drives the massive convection cells that create the planet's distinctive banded appearance. Hot material rises from the deep interior, cools as it approaches the surface, and sinks back down in vast circulation patterns that span the entire planet. These convection currents operate on timescales that dwarf human experience, with individual circulation cycles taking centuries to complete. The chemical processes occurring in these convecting layers create some of the most complex atmospheric chemistry in the solar system. Compounds that would be stable under Earth conditions are constantly being broken apart and reformed by the extreme temperatures and pressures. Simple molecules like water and methane are transformed into exotic organic compounds that exist nowhere else in our solar system naturally. Some of these reactions might even create the building blocks of more complex chemistry, though the violent conditions make it impossible for any stable structures to persist for long. The constant churning of Jupiter's interior ensures that any complex molecules are quickly broken apart and recycled through the convection system, preventing the kind of stable chemical evolution that led to life on Earth. As our journey approaches the theoretical solid core at Jupiter's center, we encounter pressures that exceed 40 million times Earth's atmospheric pressure. At these crushing intensities, the very concept of solid matter takes on new meaning. Rock and ice, if they exist here, would be compressed to densities that make them behave more like exotic metals than familiar earthly materials. The core itself remains one of the great mysteries of planetary science. Recent observations from NASA's Juno mission suggest that Jupiter's core might not be the solid, well-defined sphere that scientists once imagined. Instead, it appears to be a fuzzy, partially dissolved region where rock and metallic hydrogen mix in ways that blur the traditional boundaries between a planet's core and its surrounding layers. This discovery revolutionizes our understanding of how gas giants form and evolve. Rather than accreting around a solid seed like the terrestrial planets, Jupiter might have formed through a more gradual process where rocky material became incorporated into the growing ball of gas over millions of years. The intense heat and pressure then partially dissolved this rocky core, creating the fuzzy boundary region that Juno has detected. The implications extend far beyond Jupiter itself. If gas giants don't require solid cores to form, It changes our understanding of how planetary systems evolve around other stars. The thousands of exoplanets we've discovered orbiting distant suns might have formed through processes quite different from what we see in our own solar system. Jupiter's influence on the architecture of our solar system cannot be overstated. Its massive gravitational field has shepherded the orbits of countless smaller bodies over billions of years, creating the asteroid belt through gravitational resonances that prevent the rocky debris from coalescing into a planet. The same gravitational influence has captured families of asteroids at stable points in Jupiter's orbit, creating the Trojan asteroids that follow and precede the giant planet in its path around the Sun. The planet's moons tell their own story of tidal forces and gravitational influence. Europa's subsurface ocean, kept liquid by tidal heating from Jupiter's gravity, represents one of the most promising locations in the solar system for the search for extraterrestrial life. The same tidal forces that would tear apart any human falling toward Jupiter have created and maintained an ocean that has existed for billions of years beneath Europa's icy shell. Io, the most volcanically active body in the solar system, is literally turned inside out by Jupiter's tidal forces. The constant stretching and compression heats Io's interior to the melting point, driving sulfur volcanoes that spew material hundreds of miles into space. The yellow and orange sulfur compounds that coat Io's surface create an alien landscape that looks more like a pizza than a traditional moon. Ganymede, the largest moon in the solar system, generates its own magnetic field through processes similar to those occurring in Jupiter's metallic hydrogen core. The interaction between Ganymede's magnetic field and Jupiter's creates complex auroral displays on the moon's thin atmosphere, adding another layer to the electromagnetic symphony playing out in the Jovian system. As we contemplate the end of our impossible journey into Jupiter's heart, we're struck by the incredible complexity and beauty hidden within this giant world. What appears from space as a serene ball of swirling clouds conceals an interior more dynamic and extreme than anything found on the terrestrial planets. The same forces that would prove instantly fatal to any earthly visitor are the forces that have shaped our solar system and continue to influence its evolution today. The journey into Jupiter serves as a profound reminder of how little we truly know about the universe around us. Despite centuries of telescopic observations and decades of spacecraft missions, the interior of our solar system's largest planet remains largely mysterious. Each new discovery raises more questions than it answers, revealing layers of complexity that challenge our theoretical models and force us to reconsider our assumptions about how worlds form and evolve. Tonight, as you rest in the safety of Earth's gentle embrace, you can marvel at the fact that such extreme and alien worlds exist just next door in cosmic terms. Jupiter orbits the same star that warms our planet, formed from the same primordial disk of gas and dust that gave birth to Earth, yet evolved into something so fundamentally different that it challenges our imagination to even comprehend its true nature. The gas giant stands as a monument to the incredible diversity of worlds that populate our universe, a reminder that the cosmic story extends far beyond our familiar blue marble, into realms where matter and energy dance to rhythms we're only beginning to understand. In the quiet darkness of space, Jupiter continues its ancient orbit, harboring secrets that may take centuries more to unravel. a world that bridges the gap between planet and star, between the familiar and the utterly alien. Our theoretical fall through Jupiter's layers has taken us on a journey through states of matter that exist nowhere else in our solar system, through temperatures and pressures that push the boundaries of physics itself. It's a journey that ultimately brings us back to Earth with a deeper appreciation for the delicate balance of forces that makes our world such a rare and precious sanctuary in the vast cosmic ocean that surrounds us all. In the crushing depths, where our journey through Jupiter reaches its most extreme point, we encounter conditions so alien that they redefine our understanding of what it means for matter to exist. Here, at pressures that would instantly compress diamond into something denser than the core of a neutron star, we find ourselves in a realm where the very atoms that make up reality are forced into configurations that exist nowhere else in the known universe. The boundary between Jupiter's metallic hydrogen ocean and its mysterious core represents one of the most extreme transitions in our solar system. As we descend through this interface, the temperature climbs to levels that would make the sun's surface seem cool by comparison. The pressure becomes so intense that it warps the very structure of atoms, forcing electrons into orbits that quantum mechanics suggests should be impossible under normal circumstances. At these depths, perhaps 20,000 miles below the cloud tops where our journey began, time itself seems to slow under the weight of such crushing forces. The convection currents that drive Jupiter's atmospheric dynamics operate on geological timescales here, with material taking millennia to complete a single circulation cycle. The heat generated by gravitational compression creates temperature gradients so steep that they drive chemical processes unknown anywhere else in our solar system. The exotic matter surrounding us at Jupiter's core exists in a state that challenges every category we use to describe the phases of matter. It's neither solid nor liquid nor gas, but something altogether more fundamental, a plasma so dense and hot that it behaves according to principles we're only beginning to understand. The hydrogen atoms have been stripped not just of their electrons, but compressed to the point where the normal rules governing atomic structure simply cease to apply. This is where Jupiter's magnetic field truly originates, in the chaotic dance of charged particles moving through conditions more extreme than those found in most stellar cores. The electrical currents flowing through this impossible landscape generate magnetic field lines that spiral outward through thousands of miles of metallic hydrogen, eventually emerging into space as the powerful magnetosphere that shields Jupiter's moons from the harsh radiation of the solar wind. As we contemplate the final moments of our theoretical descent, we approach the very heart of this giant world, where pressures may exceed 50 million times Earth's atmospheric pressure. Here, in a region smaller than Earth, but containing more mass than several of our planets combined, matter exists in forms that have no names in any human language. The rock and ice that may comprise Jupiter's core have been transformed by pressure and heat into something that bears no resemblance to any earthly material. Recent discoveries suggest that this core might not be the neat, defined sphere that scientists once imagined. Instead, it appears to be a gradual transition zone where the metallic hydrogen gradually gives way to heavier elements dissolved and mixed in ways that blur the traditional boundaries between a planet's layers. This fuzzy core challenges our understanding of planetary formation, suggesting that gas giants like Jupiter might have assembled through processes quite different from the neat accretion models we once relied upon. The implications ripple outward from Jupiter's core to our understanding of planetary systems throughout the galaxy. If gas giants can form without the solid cores we once thought necessary, it opens up new possibilities for how worlds might come together around distant stars. The thousands of exoplanets discovered orbiting other suns might represent an even greater diversity of formation processes than we previously imagined. But our journey into Jupiter reveals more than just the extreme physics of planetary interiors. It illuminates the delicate web of gravitational influences that have shaped our solar system over billions of years. Jupiter's immense mass has acted as both protector and sculptor, deflecting dangerous asteroids and comets away from the inner planets, while simultaneously organizing the architecture of the outer solar system through its gravitational influence. The same tidal forces that would stretch and compress any falling object have shaped the evolution of Jupiter's moons in profound ways. The constant gravitational kneading keeps Europa's subsurface ocean liquid, Io's interior molten, and Ganymede's magnetic field active. These moons represent some of the most intriguing destinations in our search for life beyond Earth. Worlds where the energy provided by Jupiter's gravity might substitute for the solar energy that drives Earth's biosphere. The Great Red Spot, that massive anticyclonic storm we observed at the beginning of our journey, draws its energy from the same internal heat sources that create the extreme conditions in Jupiter's deep interior. This storm system has persisted for centuries, possibly much longer, sustained by the planet's internal dynamo and the complex interactions between different atmospheric layers. Its longevity speaks to the incredible stability of the energy sources driving Jupiter's atmospheric dynamics. The auroras that crown Jupiter's poles with ethereal light are powered by the interaction between the planet's magnetic field and charged particles from the solar wind. These displays dwarf anything seen on Earth, with individual auroral features larger than our entire planet, painting Jupiter's polar regions with colors invisible to human eyes but captured in stunning detail by ultraviolet telescopes orbiting Earth. As our impossible journey through Jupiter's interior draws to a close, we're left with a profound sense of the incredible forces that operate throughout our universe. The same fundamental physics that creates such extreme conditions within Jupiter also drives the nuclear fusion in stellar cores, the formation of planetary systems, and the evolution of galaxies themselves. Jupiter serves as a laboratory for understanding how matter behaves under conditions we can barely create in our most advanced particle accelerators. The journey also highlights the remarkable precision required for a world like Earth to exist, the gravitational balance that keeps our planet in a stable orbit, the atmospheric pressure that allows liquid water to persist on the surface, the magnetic field that protects us from harmful radiation. All of these factors that seem so natural and inevitable are actually incredibly rare and precious in the cosmic context that Jupiter helps us appreciate. Tonight, as you prepare to rest in the gentle embrace of Earth's familiar gravity, you can reflect on the incredible journey we've taken together through the heart of our solar system's giant. We've descended through layers of atmosphere thicker than continents, encountered forms of matter that exist nowhere else naturally, and explored conditions more extreme than those found in the cores of many stars. The peaceful point of light that you might glimpse in the evening sky hides one of the most dynamic and complex worlds in our solar system. Behind Jupiter's serene appearance lies a churning dynamo of heat and motion, a world where the fundamental forces of physics play out their drama on scales that stretch our understanding and humble our earthly perspective. Our theoretical fall into Jupiter has revealed not just the fate that would await any visitor to this giant world, but the incredible processes that have shaped our cosmic neighborhood over billions of years. In contemplating the impossible extremes hidden within Jupiter's depths, we gain a deeper appreciation for the delicate balance of forces that makes our own blue marble such a rare sanctuary in the vast ocean of space. The gas giant continues its ancient dance around our sun, harboring mysteries that may take generations to fully understand, serving as both a reminder of how much we've learned about our solar system and how much remains to be discovered. In the quiet darkness of space, Jupiter spins on, a world that bridges the gap between the familiar and the utterly alien, between the planetary and the stellar, carrying within its depths the secrets of how worlds are born and how they evolve over cosmic time. As sleep carries you away from our cosmic journey, you can rest knowing that somewhere in the night sky, this magnificent giant continues its eternal vigil, shaping the solar system through its gravitational influence, while harboring within its crushing depths some of the most extreme and beautiful physics in our corner of the universe. The electromagnetic storms that rage through Jupiter's magnetosphere create cascading effects that ripple across the entire Jovian system. These invisible tempests, driven by the planet's rapid rotation and powered by its internal dynamo, generate radiation belts so intense they would prove lethal to any spacecraft not specifically shielded against their fury. The charged particles trapped in these magnetic field lines spiral endlessly around the planet, creating an invisible cage of deadly radiation that extends millions of miles into space. As we contemplate the final stages of our theoretical descent through Jupiter's impossible landscape, we encounter phenomena that stretch the very limits of what we consider possible within the laws of physics. The material surrounding us has been transformed by pressure and heat into something that defies easy categorization, existing in quantum states that our earthly experience has no framework for understanding. Here, in the deepest reaches of this gas giant's heart, matter exists in forms so exotic that they challenge our most sophisticated theories about how atoms and molecules should behave. The temperature gradients in Jupiter's core region create convection patterns that operate on timescales beyond human comprehension. Individual currents of superheated plasma may take thousands of years to complete a single circulation cycle, carrying heat and dissolved materials through pathways that wind through the planet's interior like the bloodstream of some cosmic organism. These vast, slow rivers of molten matter help distribute the planet's internal heat outward toward the surface, maintaining the temperature differences that drive Jupiter's spectacular atmospheric dynamics. The chemical processes occurring at these depths involve reactions between elements under conditions so extreme that they create compounds unknown anywhere else in our solar system. Silicon, iron, and other heavy elements become incorporated into structures that bear no resemblance to their earthly counterparts, compressed and heated until they form crystalline lattices that exist only in the theoretical predictions of quantum mechanics. These exotic materials may hold keys to understanding how matter behaves under the most extreme conditions in the universe. The gravitational field at Jupiter's center reaches intensities that would warp space-time itself in measurable ways. According to Einstein's theory of general relativity, the curvature of space and time becomes so pronounced at these depths that clocks would run noticeably slower than they do on Earth's surface. Time itself becomes another casualty of Jupiter's immense mass, stretched and distorted by the same forces that compress matter into impossible configurations. As our imaginary journey reaches its ultimate conclusion at the very center of Jupiter's gravitational well, we find ourselves at a point where all directions lead outward, where the concept of falling loses its meaning because there is nowhere left to fall. Here, suspended in the heart of this giant world, we would be surrounded by millions of miles of compressed matter, pressing inward from every direction with equal force. The very notion of up and down becomes meaningless in this cosmic center, where the only direction that exists is outward toward the distant surface. The journey through Jupiter's interior has taken us through a catalogue of extreme states that matter can achieve when subjected to the most intense conditions our solar system has to offer. From the gossamer-thin upper atmosphere where we began our descent, through layers of ever-thickening gas, past the transition to metallic hydrogen, and finally to the exotic plasma core, we've witnessed a progression of physical states that spans nearly the entire range of conditions possible in the universe. Yet for all its extremes, Jupiter remains a relatively gentle giant compared to some of the objects that populate our cosmos. Neutron stars compress matter to densities that make Jupiter's core seem as tenuous as smoke, while black holes create gravitational fields so intense they trap light itself. Jupiter occupies a middle ground in the cosmic hierarchy of extreme environments, massive enough to create conditions impossible on Earth, yet mild compared to the most violent objects in the universe. The moons that orbit this giant world tell their own stories of gravitational influence and tidal heating. Each satellite bears the scars and signatures of Jupiter's powerful tidal forces, from Io's sulfur volcanoes to Europa's hidden ocean, from Ganymede's magnetic field to Callisto's ancient impact craters. These worlds serve as natural laboratories for studying how gravitational forces can shape entire landscapes over geological time. The radiation environment around Jupiter poses challenges that extend far beyond what any human explorer might face. The planet's magnetic field traps high-energy particles from the solar wind, creating radiation belts that would prove lethal to unprotected electronics within minutes. Spacecraft missions to the Jovian system must be carefully planned to minimize exposure to these deadly zones, threading paths between the radiation belts like navigators, avoiding reefs in treacherous waters. The atmospheric chemistry of Jupiter continues to surprise scientists with its complexity and dynamism. The Great Red Spot and other storm systems act as vast chemical reactors, mixing compounds from different atmospheric layers and creating new molecular combinations through the sheer violence of their turbulent motions. These storms may transport materials from depths of hundreds of miles up to the visible cloud tops, providing us with glimpses of the chemical processes occurring in regions we can never directly observe. The seasonal changes on Jupiter, though subtle compared to Earth's dramatic transitions, unfold over timescales that span decades. The planet's slight axial tilt and 12-year orbital period create variations in solar heating that influence atmospheric circulation patterns and storm formation. Individual weather systems may persist for years or even centuries, evolving slowly as they interact with the planet's complex atmospheric dynamics. The acoustic environment within Jupiter's atmosphere would be unlike anything experienced on Earth. Sound waves can propagate through the dense atmospheric layers, but the composition and pressure gradients would create acoustic effects impossible to reproduce in terrestrial conditions. The rumble of atmospheric turbulence, the crack of lightning discharges, and the deep bass notes of convective processes would create a symphony of alien sounds in frequencies both above and below human hearing. Jupiter's influence extends far beyond its own atmospheric boundaries, reaching out through gravitational resonances to organize the orbits of asteroids and comets throughout the outer solar system. The planet acts as a cosmic shepherd, corralling smaller bodies into stable orbital families, while deflecting others onto trajectories that carry them far from the inner planets. This gravitational gardening has helped create the relatively clean and stable environment that allowed Earth to evolve complex life over billions of years. The internal structure of Jupiter continues to reveal new mysteries as our understanding of high-pressure physics advances. Computer models suggest that the transition between different layers may be far more gradual and complex than previously imagined, with mixing zones and intermediate phases that blur the traditional boundaries between gas, liquid, and solid matter. These discoveries force us to reconsider our assumptions about how giant planets form and evolve over cosmic time. As we conclude our impossible journey through Jupiter's heart, we're reminded that this magnificent world represents just one example of the incredible diversity of environments that exist within our own solar system. The same fundamental forces that create Jupiter's extreme interior conditions operate throughout the universe, shaping worlds around distant stars and creating the cosmic laboratory in which the elements of complexity and life can emerge and flourish across the vast expanse of space and time. Tonight, as you rest under Earth's protective blanket of atmosphere and magnetic field, you can appreciate the delicate balance of forces that makes our world such a rare haven in the cosmic ocean. The journey through Jupiter's depths has shown us realms where matter behaves according to rules we're only beginning to understand, where temperatures and pressures reach extremes that challenge our most sophisticated theories, and where the fundamental forces of nature play out their eternal dance on scales both beautiful and terrifying. The gas giant continues its ancient orbit through the darkness of space, carrying within its depths secrets that may take centuries to fully unravel. In contemplating what it would mean to fall into Jupiter, we've explored not just the fate that would await any earthly visitor, but the incredible processes that have shaped our solar system and continue to influence its evolution today, reminding us that we live in a universe far stranger and more wonderful than our everyday experience could ever prepare us to imagine. Imagine the deeper mysteries of Jupiter's interior reveal themselves only through the most sophisticated computer models and theoretical physics, as no probe could ever survive the journey to witness these alien realms firsthand. As we push the boundaries of our theoretical descent beyond even the exotic core regions, we encounter phenomena that exist at the very edge of what matter can achieve under the most extreme natural conditions in our solar system. In the deepest recesses of Jupiter's gravitational well, where pressures climb to levels that dwarf even the crushing forces we've already explored, the very concept of temperature begins to take on new meaning. The kinetic energy of particles becomes so intense that individual atoms move at velocities approaching significant fractions of the speed of light. At these speeds, relativistic effects begin to influence the behavior of matter itself, creating conditions where classical physics gives way to the strange realm of quantum mechanics operating under extreme conditions. The boundary layers between Jupiter's different interior regions create zones of instability where massive convection cells rise and fall like titanic elevators carrying material between the planet's deepest core and its metallic hydrogen ocean. These circulation patterns transport not just heat and matter, but also magnetic field lines that become twisted and tangled in ways that contribute to the complex electromagnetic phenomena we observe from space. As we contemplate the ultimate fate of our theoretical journey, we must consider what happens when an object finally comes to rest at Jupiter's gravitational center. Here, suspended in perfect equilibrium with crushing forces pressing inward from every direction, matter would exist in a state unlike anything found elsewhere in nature. The hydrostatic pressure reaches levels where even the strong nuclear force that holds atomic nuclei together begins to feel the strain of compression. The electrical currents flowing through Jupiter's metallic hydrogen layers create magnetic field structures of staggering complexity. These field lines weave through the planet's interior like the strands of some cosmic spider web, carrying electrical energy in patterns that pulse and oscillate with the planet's rotation. The interaction between these internal magnetic fields and the charged particles streaming from the Sun creates the spectacular auroral displays that crown Jupiter's polar regions with light invisible to human eyes, but breathtaking in their alien beauty. The chemistry occurring in Jupiter's deep atmospheric layers involves molecular processes that push the boundaries of what we consider possible under natural conditions. Complex organic compounds form and break apart in cycles driven by the planet's internal heat and the constant churning of its atmospheric circulation. These chemical reactions occur under pressures and temperatures so extreme that they create molecular structures that exist nowhere else in our solar system. Compounds that might hold clues to understanding how complex chemistry can emerge under conditions radically different from those that gave rise to life on Earth. The tidal forces that would prove so devastating to any falling object also play a crucial role in shaping Jupiter's internal structure. The planet's rapid rotation creates centrifugal forces that work against gravity, causing the world to bulge at its equator and creating pressure gradients that influence the circulation patterns throughout its interior. This dynamic equilibrium between rotation and gravity helps maintain the stable layered structure that characterizes Jupiter's internal architecture. The acoustic properties of Jupiter's deep interior create sound propagation effects that would be impossible to experience anywhere on Earth. Pressure waves can travel through the dense metallic hydrogen layers at velocities that far exceed the speed of sound in any terrestrial material. These acoustic phenomena may play a role in transporting energy through the planet's interior, contributing to the complex heat distribution that drives Jupiter's atmospheric dynamics. The magnetic field generated in Jupiter's core reaches out across millions of miles of space, creating a magnetosphere larger than the Sun itself. This invisible shield deflects most of the charged particles streaming from our star, but it also traps some of these particles in radiation belts that spiral around the planet in complex helical patterns. The interaction between Jupiter's magnetic field and the solar wind creates a bow shock wave that extends far upstream of the planet, announcing Jupiter's presence to the charged particle environment of the solar system long before the planet itself becomes visible. The seasonal variations in Jupiter's internal heat flow, though subtle, create long-term changes in the planet's atmospheric circulation that unfold over timescales measured in Earth years. These variations may influence the formation and evolution of storm systems like the Great Red Spot, providing the energy needed to sustain these massive weather patterns over centuries or millennia. The planet's internal heat engine operates with a consistency that has remained essentially unchanged throughout human history. Yet it continues to drive atmospheric dynamics that create some of the most spectacular weather phenomena in the solar system. The gravitational waves that ripple through Jupiter's interior as massive convection cells rise and fall create subtle but measurable effects on the planet's shape and rotation. These tiny variations in Jupiter's gravitational field can be detected by sensitive spacecraft instruments, providing us with indirect evidence of the dynamic processes occurring deep within the planet's inaccessible interior. Each fluctuation in the gravitational field tells a story about convection currents and density variations that would otherwise remain completely hidden from our observation. The exotic forms of matter that exist in Jupiter's core regions may include phases of familiar elements that have been compressed into crystalline structures unknown to terrestrial science. Iron, nickel, and silicon atoms, forced into configurations that exist only under the most extreme pressures, might create materials with properties that challenge our understanding of how matter behaves when subjected to forces beyond anything we can replicate in laboratory conditions. As our theoretical journey through Jupiter's interior reaches its deepest point, we encounter the profound realization that this giant world serves as a natural laboratory for physics experiments that we could never conduct on Earth. The planet's interior contains samples of matter in states that represent some of the most extreme conditions naturally occurring in our solar system, providing insights into fundamental physics that extend far beyond planetary science into our understanding of how matter behaves throughout the universe. The convection patterns that transport heat from Jupiter's core to its surface operate according to fluid dynamics, principles scaled up to planetary proportions. Individual convection cells may be larger than Earth's entire atmosphere, rising and falling through thousands of miles of Jupiter's interior over timescales that span centuries. These massive circulation systems help explain how Jupiter can radiate more heat into space than it receives from the Sun, tapping into gravitational potential energy that has been slowly accumulating since the planet's formation billions of years ago. The pressure waves generated by Jupiter's internal convection can propagate throughout the entire planet, creating a kind of global seismic activity that has no equivalent on the terrestrial worlds. These pressure oscillations may influence everything from the planet's atmospheric circulation to the behavior of its magnetic field, coupling different regions of Jupiter's interior in ways that create feedback loops and resonance effects spanning the entire world. The chemical gradients that exist between different layers of Jupiter's interior drive diffusion processes that operate over geological timescales. Heavier elements slowly settle toward the planet's center, while lighter components rise toward the surface. But this gravitational separation is constantly disrupted by convective mixing that transports material between different regions. The balance between settling and mixing helps determine the planet's internal structure, and influences the composition of different atmospheric layers. The electromagnetic induction effects created by Jupiter's rotating magnetic field generate electrical currents not just within the planet itself, but also in its conducting moons and the charged particle environment of its magnetosphere. These induced currents create secondary magnetic fields that interact with Jupiter's primary field in complex ways, contributing to the rich electromagnetic phenomena that make the Jovian system one of the most magnetically active regions of our solar system. Tonight, as you prepare to drift into peaceful sleep, you can reflect on the incredible journey we've taken together through the heart of our solar system's most magnificent giant. We've descended through realms where matter exists in forms that challenge our understanding, where temperatures and pressures reach extremes that push the boundaries of physics itself, and where the fundamental forces of nature create conditions both beautiful and terrifying in their alien intensity. The serene point of light that Jupiter represents in our night sky conceals one of the most dynamic and complex worlds imaginable. A realm where the ordinary rules of earthly existence give way to physics so extreme it borders on the impossible. Our theoretical fall through Jupiter's layers has revealed not just the fate that would await any visitor to this giant world, but the incredible processes that continue to shape our solar system billions of years after its formation. As sleep carries you away from our cosmic exploration, you can rest in the knowledge that somewhere in the darkness above, this magnificent world continues its ancient dance around our sun, harboring within its crushing depths some of the most extreme and beautiful physics in our corner of the universe, serving as an eternal reminder of the incredible diversity and wonder that exists in the cosmic ocean that surrounds our small blue home. The journey through Jupiter's crushing embrace reveals something profound about the nature of existence itself in our universe. As we contemplate the final moments of our impossible descent, we encounter forces so fundamental they connect the smallest quantum particles to the largest cosmic structures. The same gravitational principles that would compress any earthly visitor into exotic states of matter also govern the formation of galaxies, the birth of stars, and the evolution of planetary systems throughout the cosmos. In Jupiter's deepest interior, where our theoretical journey reaches its most extreme conclusion, we find ourselves in a realm where the familiar concepts of up and down lose all meaning. Here, at the gravitational center of this massive world, every direction points outward through thousands of miles of compressed matter. The hydrostatic equilibrium that maintains Jupiter's structure creates a perfect balance of forces, where the inward pull of gravity is exactly matched by the outward pressure of compressed matter trying to expand. This balance represents one of nature's most elegant solutions to the problem of containing enormous amounts of matter in a stable configuration. Jupiter has found the perfect compromise between the relentless inward pull of its own gravity and the quantum mechanical forces that prevent matter from collapsing completely. The result is a world that has maintained its basic structure for over 4 billion years, slowly cooling and contracting as it radiates heat into the cold vacuum of space. The energy that flows outward from Jupiter's core carries with it the story of the planet's formation and evolution. Every photon of infrared radiation that escapes Jupiter's upper atmosphere began its journey in the crushing depths we've explored, carrying heat generated by the gravitational compression that occurred when the planet first formed from the primordial solar nebula. This ancient energy continues to power Jupiter's atmospheric dynamics, driving storms that dwarf anything seen on Earth and maintaining circulation patterns that have persisted for centuries. The metallic hydrogen that comprises much of Jupiter's interior exists in a state that bridges the gap between the familiar matter of everyday experience and the exotic conditions found in stellar cores. Under the immense pressures within Jupiter, hydrogen atoms are forced so close together that their electrons become delocalized, creating a metallic sea of charged particles that conducts electricity with perfect efficiency. This electron sea is what generates the powerful electrical currents that create Jupiter's magnetic field, turning the entire planet into a gigantic electromagnet. The magnetic field lines that emerge from Jupiter's interior weave through space in patterns of breathtaking complexity. These invisible threads of magnetic force extend millions of miles beyond the planet's atmosphere, creating a magnetosphere so large it could easily contain the Sun. Within this magnetic cocoon, charged particles from the solar wind become trapped, spiraling along field lines in helical trajectories that create some of the most intense radiation environments in the solar system. The interaction between Jupiter's magnetic field and its moons creates a complex electromagnetic symphony that plays out across the entire Jovian system. Io's volcanic activity is driven partly by electrical currents induced by the Moon's motion through Jupiter's magnetic field. Europa's subsurface ocean becomes slightly conductive as it moves through the same magnetic environment, creating detectable electromagnetic signatures that help scientists study the hidden sea beneath its icy crust. The gravitational influence that would prove so catastrophic to any falling visitor also serves as a cosmic sculptor, shaping the architecture of our entire solar system. Jupiter's immense mass has been clearing debris from the solar system for billions of years, either capturing asteroids and comets or flinging them into the outer darkness. This gravitational housekeeping has helped create the relatively clean environment in which Earth orbits, reducing the frequency of catastrophic impacts that might otherwise have prevented life from gaining a foothold on our world. The Trojan asteroids that share Jupiter's orbit serve as fossils from the solar system's youth, preserved in gravitational safe havens, where Jupiter's influence keeps them stable over cosmic timescales. These ancient rocky bodies may contain clues about the conditions that existed when the planets were first forming, offering us glimpses of a time when our solar system was young and chaotic, filled with debris that would eventually coalesce into the familiar worlds we see today. The Great Red Spot that has fascinated observers for centuries draws its energy from the same internal heat source that creates the extreme conditions in Jupiter's deep interior. This massive anticyclone represents a visible manifestation of the energy transport processes that occur throughout Jupiter's atmosphere, carrying heat from the planet's interior to its surface through convection cells that operate on scales difficult to comprehend. The chemical processes occurring within this great storm create compounds and molecular structures that exist nowhere else in our solar system. The violent mixing action of the storm's circulation brings materials from different atmospheric layers into contact under conditions of extreme temperature and pressure, driving chemical reactions that produce complex organic molecules. These compounds may then be transported to other regions of Jupiter's atmosphere, seeding chemical processes that extend far beyond the storm itself. The atmospheric layers through which we've traveled on our journey represent a vertical chemical laboratory where different compounds exist in distinct zones based on temperature and pressure. Ammonia clouds form in the cooler upper regions, while water ice clouds exist in the deeper, warmer layers. Between these zones, complex photochemical reactions driven by solar ultraviolet radiation create a rich tapestry of organic compounds that give Jupiter its distinctive coloration. The seasonal variations in Jupiter's atmospheric chemistry unfold over the planet's 12-year orbital period, creating subtle but measurable changes in cloud composition and storm activity. These long-term cycles may influence the formation and evolution of atmospheric features, including the appearance and disappearance of smaller storm systems that interact with the more permanent features like the Great Red Spot. The auroral displays that crown Jupiter's polar regions represent some of the most spectacular electromagnetic phenomena in our solar system. These ghostly curtains of light, invisible to human eyes but captured in stunning detail by space-based telescopes, are created by charged particles spiraling down Jupiter's magnetic field lines and colliding with atmospheric gases. The energy involved in these collisions exceeds anything seen in Earth's auroras by several orders of magnitude, creating displays that dwarf our entire planet. The radio emissions generated by Jupiter's magnetosphere can be detected by radio telescopes on Earth, providing us with a way to study the planet's magnetic field and radiation environment from millions of miles away. These radio signals carry information about the density and motion of charged particles within Jupiter's magnetosphere, allowing scientists to map the invisible electromagnetic structure that surrounds the giant planet. The gravitational waves that ripple through Jupiter's interior as convection cells rise and fall create tiny but measurable variations in the planet's shape and rotation rate. These subtle changes provide evidence of the dynamic processes occurring deep within Jupiter's inaccessible interior, offering glimpses of convection patterns and circulation systems that would otherwise remain completely hidden from observation. The tidal heating that occurs in Jupiter's moons demonstrates the far-reaching effects of the planet's gravitational influence. The same forces that would stretch and compress any falling object create internal friction within the moons themselves, generating heat that keeps Io's interior molten and Europa's ocean liquid. This gravitational energy source may be sufficient to support entire ecosystems in the hidden oceans beneath the icy surfaces of Jupiter's moons. The formation of Jupiter itself represents one of the most important events in our solar system's early history. The planet's rapid growth during the first few million years after the solar system's formation helped determine the final architecture of planetary orbits and influenced the distribution of water and other volatile compounds throughout the inner solar system. Jupiter's gravitational influence may have prevented additional planets from forming in certain regions, while helping to deliver water to Earth through the complex dance of gravitational interactions. The study of Jupiter's interior through our theoretical journey reveals the incredible precision required for a gas giant to maintain its structure over billions of years. The balance between gravitational compression and internal pressure must be maintained within narrow limits, or the planet would either collapse further or expand and lose its atmosphere to space. Jupiter has found the perfect equilibrium that allows it to radiate heat steadily while maintaining its basic structure and composition. As we conclude our impossible voyage through Jupiter's heart, we're left with a profound appreciation for the delicate balance of forces that governs planetary formation and evolution throughout the universe. The extreme conditions we've encountered exist not just within Jupiter, but in countless other worlds orbiting distant stars, each one shaped by the same fundamental physics that creates the crushing pressures and exotic matter states hidden within our solar system's largest planet. Tonight, as you rest in the gentle embrace of Earth's familiar gravity and protective atmosphere, you can marvel at the incredible diversity of worlds that populate our cosmic neighborhood. The peaceful point of light that Jupiter represents in our night sky conceals realms where matter behaves according to rules we're only beginning to understand, where the fundamental forces of nature create conditions both beautiful and alien in their intensity. The journey through Jupiter's depths has shown us that our universe contains environments so extreme they challenge our most basic assumptions about the nature of reality itself. Yet these same extreme conditions may be necessary for the formation of planetary systems like our own, creating the gravitational architecture that allows smaller, rocky worlds to form and evolve in the stable orbits where life can flourish over cosmic timescales. Our theoretical fall into Jupiter serves as a reminder that we live in a universe far stranger and more wonderful than our everyday experience could ever prepare us to imagine. The gas giant continues its ancient orbit through the darkness of space, carrying within its crushing depths some of the most extreme physics in our corner of the universe, while simultaneously serving as a guardian and sculptor of the solar system we call home. As sleep carries you away from our cosmic exploration, you can rest knowing that somewhere in the night sky above, this magnificent world continues its eternal dance around our sun, harboring mysteries that may take generations to fully understand, serving as both a testament to the incredible forces that shape worlds and a humbling reminder of how much remains to be discovered in the vast ocean of space that surrounds us all. The electromagnetic environment surrounding Jupiter creates phenomena that extend far beyond the planet's visible boundaries. As our theoretical journey reaches its deepest point, we encounter magnetic field lines so twisted and complex, they form three-dimensional knots of electromagnetic energy threading through the metallic hydrogen layers. These field lines carry electrical currents measured in millions of amperes, creating a planetary-scale electrical circuit that dwarfs any human technology. The plasma physics occurring within Jupiter's core operates according to principles that exist at the frontier of our scientific understanding. Here, in regions where matter has been stripped of familiar properties, electromagnetic forces interact with gravitational compression to create states of energy and matter that bridge the gap between planetary interiors and stellar cores. The boundary between these domains becomes blurred when pressures reach levels where conventional atomic structure begins to break down entirely. Within the deepest recesses of Jupiter's interior, quantum mechanical effects begin to dominate the behavior of matter on macroscopic scales. The Pauli exclusion principle, which normally operates only at atomic levels, starts to influence the bulk properties of matter when electrons are compressed to densities approaching those found in white dwarf stars. This quantum degeneracy pressure provides additional resistance to gravitational collapse, helping to maintain the planet's structural stability over cosmic time. The thermal gradients extending from Jupiter's core to its surface create convection patterns that operate like vast thermal engines, converting gravitational potential energy into kinetic energy with an efficiency that would be impossible to achieve through any artificial process. These natural heat engines have been operating continuously for over 4 billion years, powered by the slow gravitational contraction that occurs as Jupiter gradually cools and shrinks by microscopic amounts each year. The isotopic composition of elements within Jupiter's deep interior tells the story of the solar system's formation in exquisite detail. Heavy elements that sank toward the planet's center during its early evolution carry chemical signatures from the primordial solar nebula, preserving information about conditions that existed before the planets formed. These chemical fossils remain locked within Jupiter's core, inaccessible to direct study, but influencing the planet's overall density and gravitational field in ways that spacecraft can detect. The seismic waves that propagate through Jupiter's interior create a form of planetary music, with acoustic frequencies determined by the planet's internal structure and composition. These sound waves, generated by convective turbulence and thermal instabilities, travel through different layers at velocities that depend on temperature, pressure, and chemical composition. The resulting acoustic signatures could theoretically be used to map Jupiter's interior structure, much as seismology reveals Earth's hidden layers. The crystalline structures that form under the extreme pressures of Jupiter's core region represent phases of matter that exist nowhere else naturally in our solar system. Familiar minerals like olivine and pyroxene become transformed into dense, high-pressure polymorphs with properties that challenge our understanding of solid-state physics. These exotic crystal phases may conduct heat and electricity in ways that influence the planet's magnetic field generation and thermal evolution. The chemical differentiation that has occurred within Jupiter over billions of years creates distinct layers with different compositions and properties. Helium, being slightly denser than hydrogen under these extreme conditions, has gradually settled toward the planet's center, releasing gravitational potential energy that contributes to Jupiter's internal heat source. This ongoing helium rain represents a slow but steady energy source that will continue for billions of years into the future. The turbulent mixing that occurs at the boundaries between different interior layers creates instabilities that can propagate outward through thousands of miles of Jupiter's atmosphere. These deep-seated disturbances may influence the formation and evolution of atmospheric features visible from space, connecting the planet's hidden interior to the dynamic weather patterns we can observe through telescopes. The magnetic field reversals that may occur within Jupiter's metallic hydrogen dynamo could dramatically alter the planet's magnetosphere over timescales of thousands or millions of years. Such reversals would temporarily weaken the magnetic shield that protects Jupiter's moons from solar radiation, potentially affecting the evolution of any ecosystems that might exist in their subsurface oceans. The gravitational focusing effects created by Jupiter's immense mass bend the paths of photons passing near the planet, creating subtle but measurable distortions in the light from background stars. These gravitational lensing effects provide another way to study Jupiter's mass distribution and internal structure, offering insights into regions that remain forever beyond the reach of direct exploration. The tidal dissipation that occurs within Jupiter's interior as the planet flexes slightly in response to gravitational forces from its largest moons generates additional heat that contributes to the planet's energy budget. This mutual tidal interaction has been gradually changing the orbits of Jupiter's moons over billions of years, slowly pushing them outward, while simultaneously slowing Jupiter's rotation by infinitesimal amounts. The phase transitions that occur at different depths within Jupiter create boundaries where the physical properties of matter change dramatically over relatively small distances. These transition zones may act as barriers to convection, creating separate circulation systems that operate independently in different regions of the planet's interior. Understanding these phase boundaries is crucial for developing accurate models of Jupiter's internal structure and evolution. The supercritical fluids that exist in Jupiter's intermediate layers exhibit properties that are neither truly liquid nor gaseous, creating unique transport phenomena for heat, momentum, and chemical species. These supercritical phases allow for efficient mixing between different atmospheric layers, while maintaining distinct chemical gradients that influence the planet's overall composition profile. The nuclear processes that may occur within Jupiter's core, though far less intense than those in stellar interiors, could still produce detectable quantities of rare isotopes through slow fusion reactions involving the heaviest elements present. These nuclear signatures would provide direct evidence of the extreme conditions existing in the planet's deepest regions, offering another window into the physics of planetary cores. The magneto-hydrodynamic waves that propagate through Jupiter's conducting interior couple the planet's magnetic field to its internal fluid motions, creating complex feedback loops between electromagnetic and mechanical processes. These interactions help regulate the strength and stability of Jupiter's magnetic field, while influencing the planet's internal circulation patterns in ways that are only beginning to be understood. The equation of state governing matter under the extreme conditions within Jupiter's interior involves physics that pushes the boundaries of our theoretical understanding. Computer models must account for quantum mechanical effects, relativistic corrections, and complex many-body interactions between particles compressed to densities approaching nuclear matter. These calculations represent some of the most challenging problems in computational physics. The chemical evolution that continues within Jupiter's interior involves reactions between trace elements under conditions so extreme that they create molecular species unknown in terrestrial chemistry. These exotic compounds may play important roles in determining the planet's thermal properties and electrical conductivity, influencing everything from magnetic field generation to atmospheric circulation patterns. The gravitational binding energy that holds Jupiter together represents a reservoir of potential energy larger than the total energy output of our Sun over millions of years. This enormous energy reserve continues to power the planet's internal dynamics and atmospheric circulation, ensuring that Jupiter will remain an active, dynamic world for billions of years into the future. The pressure-induced phase changes that transform familiar materials into exotic states within Jupiter's interior create discontinuities in density and other physical properties that influence seismic wave propagation and convective heat transfer. These phase boundaries may create distinct chemical reservoirs within the planet, preserving information about Jupiter's formation and early evolution in ways that remain accessible through careful analysis of the planet's gravitational field and magnetic properties. As our impossible journey through Jupiter's crushing heart reaches its final conclusion, we encounter the humbling realization that this magnificent world represents just one example of the incredible diversity of planetary environments that exist throughout our universe. The extreme physics we've explored within Jupiter's interior operates according to the same fundamental principles that govern matter and energy throughout the cosmos, from the cores of distant exoplanets to the hearts of binary star systems, where matter exists under even more extreme conditions. The knowledge we've gained through our theoretical descent illuminates not just the nature of gas giant interiors, but the broader processes that shape planetary formation and evolution throughout the galaxy. Every discovery about Jupiter's internal structure helps us understand how similar worlds might behave around other stars, expanding our perspective on the incredible variety of environments where matter can exist and evolve over cosmic time. Tonight, as you drift toward peaceful rest beneath Earth's protective atmosphere, you carry with you the memory of our journey through realms where the fundamental forces of nature create conditions both beautiful and terrifying in their alien intensity. The gentle pull of gravity that keeps you safely anchored to our planet's surface is the same force that, when concentrated in Jupiter's immense mass, creates the crushing pressures and exotic matter states we've explored together. The serene point of light that Jupiter represents in our night sky will forever carry new meaning for you, knowing that it conceals within its depths some of the most extreme physics naturally occurring in our solar system. Our theoretical fall through Jupiter's layers has revealed not just the incredible forces that shape giant worlds, but the delicate balance of conditions that makes our own Earth such a rare and precious sanctuary in the vast cosmic ocean. As sleep carries you gently away from our exploration, you can rest in the knowledge that somewhere above in the darkness, this magnificent giant continues its ancient dance around our sun, harboring within its crushing embrace mysteries that connect the smallest scales of quantum mechanics to the grandest structures of the cosmos, serving as an eternal reminder of the incredible wonders that await discovery in the universe we call home. The journey through Jupiter's crushing depths reveals something profound about the delicate threads that connect all matter in our universe. As we contemplate the end of our impossible descent, we find ourselves witnessing the fundamental forces that govern not just this alien world, but every atom, every star, every galaxy spinning through the cosmic darkness. The same quantum mechanical principles that create exotic matter states in Jupiter's core also determine the behavior of electrons in the atoms that make up your body. The same gravitational forces that would compress any visitor into unrecognizable forms also guide the gentle orbit of our moon around Earth. The electromagnetic phenomena we've encountered in Jupiter's metallic hydrogen layers operate on principles that extend far beyond this single world. Similar dynamo effects generate magnetic fields in planets throughout our galaxy, creating protective shields that may determine which worlds can maintain atmospheres suitable for life. The plasma physics occurring within Jupiter's interior provides insights into stellar cores, where nuclear fusion transforms hydrogen into the heavier elements that eventually become incorporated into rocky planets and living beings. As we trace the final moments of our theoretical fall toward Jupiter's gravitational center, we encounter a realm where time itself becomes distorted by the immense curvature of space-time. According to Einstein's theory of general relativity, clocks would run measurably slower in Jupiter's deep interior compared to those on Earth's surface. This temporal distortion represents a direct consequence of the mass energy that gives Jupiter its gravitational influence, connecting our journey through this gas giant to the fundamental structure of reality itself. The convection patterns that transport heat through Jupiter's interior operate according to fluid dynamics principles that scale from the microscopic to the cosmic. Individual convection cells within Jupiter may contain more mass than several Earth-sized worlds, yet they follow the same basic physical laws that govern the circulation of air in our planet's atmosphere, or the flow of magma beneath its surface. These universal principles ensure that similar processes occur throughout the universe, wherever sufficient temperature gradients and fluid materials exist. The chemical gradients we've encountered during our descent through Jupiter's atmosphere reveal the ongoing story of element formation and distribution throughout the solar system. The heavy elements concentrated in Jupiter's core were forged in the nuclear furnaces of ancient stars that lived and died before our solar system formed. These stellar remnants became incorporated into the primordial disk of gas and dust that eventually collapsed to form the Sun and planets, carrying with them the chemical signatures of cosmic processes that occurred billions of years ago. The tidal forces that would prove so destructive to any falling visitor also demonstrate the interconnected nature of gravitational systems throughout the universe. The same differential gravitational effects that create tidal heating in Jupiter's moons also shape the evolution of binary star systems, influence the formation of galactic structures, and determine the fate of matter falling into black holes. These tidal phenomena represent manifestations of gravity's influence across vast ranges of scale, from planetary systems to the largest structures in the observable universe. The radiation environment surrounding Jupiter creates a natural laboratory for studying high-energy particle physics under conditions impossible to replicate on Earth. The charged particles trapped in Jupiter's magnetosphere undergo acceleration and interaction processes similar to those occurring in cosmic ray showers, supernova remnants, and the vicinity of active galactic nuclei. Understanding these electromagnetic phenomena helps us interpret observations of similar processes occurring throughout the cosmos. The acoustic waves propagating through Jupiter's interior carry information about the planet's internal structure encoded in their frequencies and propagation speeds. This seismic exploration technique, known as helioseismology when applied to the Sun, allows scientists to probe the hidden interiors of celestial bodies throughout the universe. The same principles that would allow us to map Jupiter's core structure through acoustic analysis also enable us to study the internal dynamics of distant stars and understand the processes occurring within their nuclear-burning cores. The exotic phases of matter existing within Jupiter's deep interior may provide insights into the behavior of materials under extreme conditions throughout the universe. Similar high-pressure, high-temperature environments exist within the cores of terrestrial exoplanets, the mantles of super-Earth worlds, and the crusts of neutron stars. Understanding how familiar elements behave under Jupiter's extreme conditions helps us model the internal structure and evolution of worlds we can never directly observe. The magnetic field generation occurring within Jupiter's metallic hydrogen layers demonstrates the dynamo processes that create magnetic fields around planets, stars, and galaxies throughout the cosmos. These electromagnetic phenomena play crucial roles in determining which worlds can maintain stable atmospheres, how stellar winds interact with planetary systems, and how charged particles propagate through interstellar space. Jupiter's magnetosphere serves as an accessible example of electromagnetic processes operating on scales from planetary to galactic. The energy transport mechanisms operating within Jupiter's interior illustrate the fundamental ways that heat flows through cosmic structures. Convection, radiation, and conduction work together to distribute energy from Jupiter's core to its surface, following the same thermodynamic principles that govern heat flow within stellar interiors, planetary atmospheres, and the diffuse medium between galaxies. These energy transport processes help determine the evolutionary timescales and observable properties of celestial objects throughout the universe. The chemical differentiation that has occurred within Jupiter over billions of years demonstrates how gravitational separation processes operate in cosmic environments. Similar density-driven segregation occurs within the cores of terrestrial planets, the interiors of asteroids and comets, and even within the structure of galaxies themselves, where different types of matter become distributed according to their gravitational interactions and physical properties. The phase transitions occurring at various depths within Jupiter create boundaries where the physical state of matter changes dramatically over relatively small distances. Similar phase changes occur throughout the universe, wherever temperature and pressure conditions cross critical thresholds, from the surfaces of ice-covered moons to the photospheres of variable stars, to the shock fronts created by supernova explosions propagating through interstellar gas. The gravitational focusing effects created by Jupiter's mass demonstrate how massive objects bend the paths of light and other forms of electromagnetic radiation. These gravitational lensing phenomena operate on scales ranging from individual planets to galaxy clusters, providing astronomers with powerful tools for studying distant objects and mapping the distribution of dark matter throughout the universe. Jupiter's gravitational field serves as a local example of space-time curvature effects that operate throughout the cosmos. The thermal evolution occurring within Jupiter's interior follows principles that govern the long-term behavior of self-gravitating systems throughout the universe. The gradual cooling and contraction that Jupiter undergoes as it radiates energy into space represents a scaled-down version of the processes that determine stellar lifetimes, the evolution of brown dwarf objects, and the ultimate fate of massive cosmic structures as the universe continues to expand and cool over cosmic time. The isotopic ratios preserved within Jupiter's deep interior carry chemical fingerprints from the early solar system, providing information about the nucleosynthetic processes that occurred in previous generations of stars. These chemical signatures help us understand how elements are created, distributed, and recycled throughout galactic ecosystems, connecting Jupiter's formation to the broader story of cosmic chemical evolution that has been occurring for over 13 billion years. The magnetohydrodynamic processes occurring within Jupiter's conducting interior demonstrate how magnetic fields interact with flowing plasma under extreme conditions. Similar magnetohydrodynamic phenomena govern the behavior of stellar atmospheres, the structure of planetary magnetospheres, the dynamics of accretion disks around compact objects, and the propagation of magnetic fields through the ionized medium of interstellar space. The gravitational binding energy that holds Jupiter together represents a fundamental measure of the work required to assemble massive objects from dispersed matter. This binding energy concept applies to structures throughout the universe, from asteroids and planets to star clusters and galaxy groups, helping us understand how gravitational forces shape the hierarchical structure of matter on all scales, from planetary to cosmic. As our theoretical journey through Jupiter's heart reaches its deepest conclusion, we encounter the profound realization that the extreme conditions within this gas giant connect us to some of the most fundamental processes operating throughout the universe. The crushing pressures, exotic matter states, and electromagnetic phenomena we've explored represent local examples of physics that governs everything from the cores of distant exoplanets to the event horizons of black holes. The knowledge gained through our impossible descent illuminates not just the nature of Jupiter's interior, but the universal principles that shape matter and energy throughout cosmic history. Every aspect of Jupiter's internal structure reflects the operation of physical laws that determine how complexity emerges from simplicity, how order arises from chaos, and how the same fundamental forces create both the gentle conditions that allow life to flourish on Earth and the extreme environments that forge elements in stellar cores. Tonight, as you rest in the embrace of Earth's familiar gravity, you carry with you an appreciation for the incredible journey we've shared through realms where matter behaves according to principles we're only beginning to understand. The peaceful darkness above conceals worlds where the fundamental forces of nature create conditions that challenge our imagination, while simultaneously demonstrating the elegant unity underlying all physical phenomena. The gas giant continues its eternal orbit through space, carrying within its depths secrets that connect the quantum realm to cosmic structures, the microscopic to the magnificent, the familiar to the utterly alien. Our fall through Jupiter's crushing embrace has revealed not just the extreme physics hidden within a single world, but the beautiful interconnectedness of all matter and energy dancing through the vast symphony of existence itself. As sleep gently carries you away from our cosmic exploration, you can rest knowing that the same atoms forged in ancient stellar cores that now comprise Jupiter's exotic interior also flow through your veins, connecting you intimately to the grand story of cosmic evolution that continues to unfold across the immense scales of space and time that surround our small but precious corner of the infinite universe. The final chapter of our descent reveals Jupiter's most profound secret, one that connects this crushing world to the very heartbeat of cosmic evolution itself. As we approach the theoretical endpoint of our impossible journey, we encounter conditions so extreme they exist at the boundary between matter and energy, where the familiar categories of solid, liquid, and gas dissolve into something far more fundamental and mysterious. At the very center of Jupiter's gravitational embrace, where all directions point outward and the concept of falling becomes meaningless, we find ourselves suspended in a realm where quantum mechanics and general relativity converge in ways that challenge our deepest understanding of reality. Here, surrounded by millions of miles of compressed matter pressing inward with unimaginable force, the hydrogen that began as simple gas molecules has been transformed into something that exists nowhere else naturally in our solar system. The electrons in this central region have been pressed so close to atomic nuclei that they begin to merge in ways that blur the distinction between matter and energy. This is not the nuclear fusion that powers stars, but something more subtle and strange. A quantum mechanical dance where particles exist in superposition states that would be impossible under any earthly conditions. The very atoms that make up this exotic core may flicker between different configurations faster than time itself can be measured. The temperature at Jupiter's heart reaches levels that dwarf the surface of most stars. Yet the crushing pressure prevents this energy from expanding outward in the explosive fusion reactions that illuminate stellar cores. Instead, This thermal energy becomes locked in a delicate balance with gravitational compression, creating a stable configuration that has persisted for billions of years, while slowly radiating heat through thousands of miles of dense atmosphere. The magnetic field lines that originate in these central regions carry information about conditions so extreme that they exist beyond the reach of any earthly experiment. These electromagnetic phenomena propagate outward through Jupiter's metallic hydrogen layers like messages from an alien realm, eventually emerging into space as the powerful magnetosphere that has been shaping the evolution of the Jovian system for cosmic ages. As our theoretical journey reaches its absolute conclusion at the gravitational center of this magnificent world, we encounter the humbling realization that Jupiter serves as a bridge between the planetary and stellar realms. This gas giant represents what our solar system might have become if conditions during its formation had been slightly different. If Jupiter had gathered just enough additional mass to ignite the nuclear fires that would have transformed our cosmic neighborhood into a binary star system, the exotic matter states we've encountered in Jupiter's deepest interior may provide clues about the behavior of materials under conditions that exist throughout the universe. From the cores of massive exoplanets to the surfaces of neutron stars, where matter is compressed to densities beyond anything found in our solar system. Understanding Jupiter's internal physics helps us decode the secrets of worlds we can never visit, expanding our knowledge of planetary formation and evolution throughout the galaxy. The energy that flows continuously outward from Jupiter's core represents a fossil remnant from the planet's violent birth, when gravitational collapse heated this world to temperatures exceeding those found on the Sun's surface. This ancient heat continues to power atmospheric dynamics that create some of the most spectacular weather phenomena in our solar system. Storms that have raged for centuries and circulation patterns that transport energy across planetary distances. And so our impossible journey through Jupiter's heart comes to its gentle end, leaving us with a profound sense of wonder at the incredible forces that shape our cosmic neighborhood. We've descended through layers of atmosphere thicker than continents, encountered forms of matter that exist nowhere else in nature, and witnessed conditions more extreme than those found in the cores of distant stars. Tonight, as you rest safely in Earth's embrace, you can marvel at how this peaceful point of light in our evening sky conceals one of the universe's most magnificent laboratories, where the fundamental forces of nature create both beauty and terror on scales that humble our earthly perspective, reminding us that we live in a cosmos far more wondrous and strange than we ever dared imagine.